Good. Welcome, everybody, to today's CAR showroom. This is the CAR showrooms are a series of seminars that have been running at Cambridge Architectural Research since the earliest one in 1991. We're coming up to getting close to our 200th. Since COVID, we do them online, and that's one of the bonuses of the COVID disruption is that we're able to welcome many more people from a much wider spread. So if anybody's either far west and having to get up very early in the morning, or far east having to stay up late at night, thank you for joining us. The showrooms are forums for us to present work done within Cambridge Architectural Research by our own directors or by guests on a variety of topics. CAR is a multidisciplinary organisation, so there's a wide range of themes. Today's session is by two in-house session, two of our directors. Francesco Pellisari, relatively recently joined CAR as a director. He's an acoustician and has very innovative and experimental ideas about acoustics. He isn't stuck in any ruts in his approach, and I think you'll find out today that he approaches things in a technically adventurous way. And the second presenter is Jason Palmer. He's been a director at CAR for much longer, since 2003. He specialises in energy work, energy modelling, energy monitoring, and the two of them together are launching this very interesting study on acoustics and heat pumps. And I think I better hand over and let them take it away and tell us all about it.
Fantastic, thank you, William. So yes, welcome everyone. I think you know that we're here to talk about heat pumps and acoustics, and the way the presentation breaks down in these 5 sections, we're going to start off by putting the work into context by talking about the current policy drivers, why it is that the UK government is currently pushing heat pumps so hard, and a bit about the legal context as well, current legal restrictions that apply to heat pumps in homes and other buildings. Then we're not going to dwell on or go into in any detail the technical side of heat pumps. You can find information about that elsewhere, but suffice it to say there are 3 different kinds of air source heat pumps, and we're focusing today on air source heat pumps. The first sort are monoblock heat pumps, where both the fans and compressor are located outside, and there's a hot water circuit that transfers energy between outside the building and inside the building. The second sort is a split system air source heat pump, where you have an external unit with the fans, which drives a refrigeration circuit that moves the energy inside the home, and then inside the home or building are the compressors. So you have 2 separate units, each of which potentially can create noise. And then the third type is an air-to-air heat pump, where again you have 2 units, one internally, one externally, but the difference here is that there is no wet heating circuit, so there are no radiators, and you'll see later on in the presentation photographs of what the internal unit looks like. You've probably come across this air-to-air heat pump system in hotels, and some offices have these types of heating system. So we're going to cover each of these three sorts. We have case studies of each of the 3 types of heat pumps, and we're going to take you through the findings from each of those case studies, and then we're going to describe how you can reduce noise generated by all 3 types. Okay, firstly then, by way of background, the UK government, you may know, is really committed to driving up the number of heat pumps that are being installed in UK buildings at the moment. And the reason the UK government is so firm in trying to push heat pumps is because this is a critical way of reducing carbon emissions from buildings. Our work for BAYES suggests that you can reduce carbon emissions from heating a home from on average of 2.5 tonnes per house down to 0.8 tonnes per dwelling per year. That's a reduction of 2/3 by switching over from gas heating to a heat pump. And that's with current day carbon factors from electricity. As those carbon emissions factors from electricity fall over time, that 0.8 tonnes per dwelling will fall still further. So it's really, really important way that we can be reducing carbon emissions and help to address climate change. So the government is committed to scaling up deployment of heat pumps up to 600,000 a year from the current level of about 30,000 a year. And it also, at the same time, wants to dramatically bring down the costs of heat pumps. All this is described in quite some detail in the heat and building strategy, which was published late last year after some delays. It was an eagerly awaited report explaining how we'll meet the 2050 carbon reduction target. And it talks in enormous detail about heat pumps, but says nothing about noise. On the other hand, the legal backdrop for heat pumps does say quite a lot about noise, and the restrictions on permitted development currently states that you're allowed to install a heat pump so long as it emits less than 42 dBA. And 42 dBA, prosaically, is about the same level of noise as birdsong. Alternatively, not quite so figuratively, it's roughly the same volume of noise as you would experience the other side of a fence from a road. Statutory nuisance is a stricter target, and this is the noise level where local authorities would intervene to deal with a noise problem, and that's normally defined as above 34 dBA, or alternatively, if there are other sorts of noise, it's 10 dBA above the background noise. So these limits are important legislative limits, and we'll say something about how these relate to heat pumps. But the significant one, the key point about these thresholds defined in dBA is that these are weighted measures of noise. Decibels are a logarithmic scale, so 10 decibels roughly equates to a tripling of sound pressure, or something like what you'd experience as a doubling of volume. So it's a big difference between 34 and 42 dBA, but the catch is that this is averaged across all frequencies. And the critical point we want to make is that actually people experience frequencies, different frequencies differently. And this is a key consideration when it comes to noise problems.
Okay, yes, this is about the human and the animal. It's very important to understand when you make the measurement in dBA, you basically cut all noise between 20 Hertz and 500 Hertz and 10,000 Hertz up. So basically what you measure is only 500 to 10 kilohertz. But what's happened in a different frequency? For example, the dog is very sensible around 18, 20 kilohertz. And the children also is very sensible for the high frequency. And about the low frequency is a very precise message for the dog, is an order. So for example, if you have some low frequency around 50 Hertz, for the dog is increase the anxiety. So this is very important to understand the way to take the measurement and the different from the low when talk about the dBA measurement.
We're primarily interested in humans, of course, and the first system we looked at was a monoblock installation. This is where all of the heat pump equipment is located externally outside a house, and this is a Victorian, quite a large Victorian property in Cambridge, which has, as you can imagine, a large heat pump attached to it, 16 kilowatts. So that's bigger than the most heat pumps in homes would be installed. And there were a couple of unusual features about this heat pump system. The first one is that it's not meeting both domestic hot water demand and space heating. This heat pump solely produces space heating, and there's an alternative heating system. It's actually the old gas boiler, which is currently being used to produce domestic hot water. As I said, the heat pump is outside. There is some a buffer vessel and various other gubbins internally. I might say in passing, not on the acoustics side so much, but thanks to Nicola Terry, we have these really useful measurements of the achieved coefficient of performance. And this is the single most important measure about energy efficiency of a heat pump. And you can see these are daily readings. Each point on this chart is a daily COP. And you can see the average there is about 3.4. So you're getting roughly 3.4 units of heating out for every 1 unit of electricity that goes in. And this is more or less what we would expect from a good air source heat pump. On the acoustic side.
Yes, so in this case, the frequency response is without any filter. And in fact, we start at 10 Hertz and to 20 kilohertz. And we can see the pitch at around 17 kilohertz.
That's a peak at 17.
Peak,
16
sorry,
kilohertz.
16 kilohertz, a peak. What for the many people is not a problem because it's a very high frequency. But this type of frequency, for example, is a very big issue for the children and a big issue for the cat and the dog. And also we have another peak at the low frequency, around 40 Hertz and around 80 Hertz. 32 and 71, but anyway, don't make many difference. In this case, this frequency can give you a headache and a problem from the school of the bone in your school. So it's not the here the problem, but it's that your school receive this frequency. This basically is the inside the house. And again, we have the 16 kilohertz, basically without any attenuation. So this means this type of sound comes from the pipe or some mechanical connection.
So the bottom line of that in that situation was the occupants were unconcerned. They weren't actually bothered at all by the noise generated by this system. That might be partly because they were older. And I think Francesco touched on this, that later in life, people's hearing deteriorates, and particularly people's sensitivity to higher frequencies declines. So in this instance, there's absolutely no problem at all. There were no real concerns about the acoustic impact. Moving on to another system, and the split system, where you have fans located externally, compressor pumps internally. This is actually becoming quite common in new housing now. And this is a new housing development we looked at of flats, where you can see here there are heat pumps located on the roof of the flat. You can see top right in the slide. And these heat pumps have actually rigid pipework connecting them internally to the plant room on the ground floor of the building. You see these large compressors bottom right that were located in the plant room. Both of these were causing some noise, and there were noise issues and some disturbance caused by noise in these locations.
Okay, in this case, the noise is very high, and in fact, also the human receive the impact of the noise, because we have a very high pitch at around 500 Hertz. If 500 Hertz is a type of noise, can give you a big issue. There is another problem in the low frequency, what is very high. And this low frequency go to the pipe, because unfortunately the pipe don't have any venturi pipe and any damping. So basically this noise comes from the system in the basement and go to the pipe to the roof. After this vibration from the pump go to the roof of the house. So basically the people live in this house receive a vibration, mechanical vibration all day. And of course, this is a problem, a very big impact. Again, also here we have a high frequency pitch at 16 kilohertz. This is the electronic made this problem. And this is the measurement in the basement. And in fact, we have exactly the same pitch frequency, low frequency, and we have a bigger pitch around 50 hertz, another around 500 hertz, and another at 16 kilohertz. What exactly the same frequency we measurement in the roof. This is the system in the basement, and where basically produce the 80% of the energy. And all this energy don't have any dump. So basically all energy with the pipe, rigid connect, go upstairs. It's possible to increase, improve the quality of the life if when you install the system, think before the way to install and use the right method. So basically dumping material and Helmholtz resonance and the Venturi pipe, basically what usually need to do. But in this case, I don't know why, but there is no any this type of installation. It's just a direct and mechanical connect.
So a couple other points. This is the absolute classic installation on the roof. You can see here that the heat pumps are located top right on flexi-foot fixings placed on concrete blocks. And you know that's an absolute classic way of installing this kind of equipment, as it is for air conditioning systems. So externally, they've thought a little bit about acoustics, but they haven't really given it sufficient emphasis. And the rigid pipework definitely works against them.
Is a problem, yeah.
Whereas internally, it doesn't seem as if that same thought on the acoustic side has been carried over at all. And the supports, you can see bottom right in the image for the compressors are very flimsy and have no damping at all, as Francesco says. Okay, the next split system we looked at was for terraced housing, and in this development there were sometimes apartments one on top of the other, and sometimes terraced houses. In the case of the apartments, there would be two heat pumps located on the ground floor serving the apartment above and the apartment below. In the case of houses, there will be a single heat pump serving the whole dwelling. Each dwelling basically has its own heat pump, and you can see this is quite nice, quite attractive screening here. There's 1.1 meter high brick walls, which helped a lot from the aesthetic perspective and the visual angle, but as we'll hear, didn't do quite such a good job on the acoustic side.
So we have a similar problem with a different frequency because, of course, the distance is reduced and the dimension is reduced. And we, again, have a pitch around at 40 hertz and a 180 hertz. And we don't have no problem at a high frequency. The problem of this is not the quantity of the energy, what is not very much. Also, the place is near to the output. So in reality, you already receive the noise from the output. But the difference is the noise from the output is a completely random in all frequency. And basically low frequency, but without any pitch. So it's not very disturbing. What is a problem is when you have the pitch with a single frequency, this start to make a resonance, and the resonance go to the pipe and go inside the house. So what's happened in reality is not the noise directly, but is a resonance go inside the splitter in the house, and you receive this noise vibration all day. This make the problem.
not just in the daytime, particularly at night.
In the night, of course, it's like, it's very similar if you think about a mosquito. Mosquito noise is incredible low in terms of energy. Mosquito is around, I don't know, 15, 20 dB. So it's a very low, but because it's a specific frequency, you start go mad when you have a mosquito in the room. You start to wake up, you try kill immediately the mosquito because it's very nervous, because it's a single frequency. This is a big difference. This is a comparison between the noise from the outer root and the noise from the pump. And if you see, basically the energy is the same. The only difference is from the pump, you have the pitch. And from the outer root, you don't have any pitch. This is why you receive more problem from the pump in comparison to the traffic. This is basically some solution. What in this case, there is a case, the metal frame start vibration. So of course you need stop the vibration of the case and need to stop the resonance go to the pipe. This is the best way.
So the main point about some of these fixes is that the cost is tiny, absolutely.
No, absolutely. The cost is very, very, if you think in advance, the cost is nothing, basically, because if you think in advance as a good way to install a pump, in reality, you need only to do in a good way, don't have any cost. Resolve after is very different, is very, very different. Usually resolve after increase the cost. Of course, depend what you need to do. But for example, after we see the problem in Italy, I resolved it 1 month ago, and unfortunately, the architect need to invest a lot of money for resolve.
Okay, the final case study then is of an air-to-air heat pump, and this is a system where you have, this is the external unit. You can see it's quite a small unit, 2.5 kilowatts size, just providing heating for one room with some sort of incidental gain in other rooms. And you can see in the photo on the right here, you can see the internal units. And this is the system that is similar to a system you would have experienced in hotels and some offices. And you can see actually the picture on the left does just about show where the external unit is located, just outside the window. It's 50 mil from the back wall. And there is a transfer of refrigerant from the unit outside to the unit inside. There's a small fan in the unit outside. The internal unit has 4 speeds. At the lowest setting, it's basically inaudible, and then it slowly ramps up so that the fourth speed, which actually the occupants never use, it does become somewhat noisy.
Yes, for example, in this case, the noise inside is very low. Why? Because the pump is not fixed with a slab, but is fixed directly on the soil. So the soil absorbs the vibration. Also, the pipe external is connected with a very short pipe and damping pipe. So in this way, the vibration from the pump don't go to the split internal. In fact, the internal noise is 28 dB, what is very, very low. We have only one pitch at around 70, 80 Hertz, what is around 50 dB. And if this house, for example, have a dog, this can make a problem for the dog, but not for the human. External is completely different. External, honestly, for me, was impossible survive for 10 minutes. External, the noise is very high for me because at the low frequency, we have 54 dB, what is a lot. And also there is a very high peak at 17, 18 kilohertz. What unfortunately, I'm very sensible at this frequency. So for me, is absolutely impossible. But this frequency is a very disturbing also for the cat and for the dog and for the children. When you have 3 months, 4 months, 5 months, this type of frequency is very, very sensible. And you can have the children cry, don't sleep well, etc. You don't know why. This is one of the typical problems. This again is external noise at a 3-meter distance. And if you see at a 3-meter distance, you have more interference from the wall, what is usual. And again, you have the pitch at 17, 18 kilohertz. This is not reduced at all. So this means this frequency is near omnidirectional from the electronic components. This is a comparison. So the red and the orange is two measurement, front and back and lateral, because back was impossible. In the garden, and you have the pitch at high frequency, 17 kilohertz, and the blue is inside the house. And if you see, the picture is completely out, so the high frequency don't go inside. This is because the pipe is connected in a good way. Also, if the pump is very near, because the pump is around 20 centimeters from the window, but the window is a 3-layer window, very, very good quality. And the pipe is damping, so the high frequency don't go inside completely. You have only the low frequency, again, the 70 hertz. It is come from directly from the liquid to the pump and the mechanical vibration in the splitter. So basically, what we already said, the occupant don't have any problem. The internal noise is basically low, the 30 dB, so it's basically not possible to listen. And for him, it's not a problem because he's a person up 50-year-old, so don't have any problem for the high frequency. But also don't have any pet. This is a big difference, because if you have a pet, 17 kilohertz is a very big problem, very, very huge problem. Also for the children or baby, I don't know no, maybe baby. Anyway, when the children have some months, because after 1 year, 1.5 years, reduce a lot of these sensible.
Yes, so as Francesco says, this is not currently a problem whatsoever, but there are questions about what happens to this house if the current occupants move out, somebody else moves in, they've got a younger family, they've got young children, or similarly if their neighbours, currently their neighbours are also elderly, probably have also lost some of the high frequency hearing. Again, not inconvenienced and don't especially notice the noise in their garden. But that might all change if somebody younger moves in, and if they find that they are more sensitive to noise at those frequencies. One of the points about the air-to-air heat pumps is that these aren't providing hot water. So they would ordinarily only be used in the winter to provide heating. It's possible they could be used for cooling as well, but let's not go into that now. But what this means is that when people are using their gardens more, both the occupants and their neighbours, actually they're much less likely to be inconvenienced by noise in their garden, and that's unlikely to be an issue. Okay, so what happens if you have an existing noise problem that you need to try to address? There are a couple of different ways you can
Okay.
proceed.
This is what I use in Italy, was a tube pump around 15 kilowatt, and the noise go inside the swimming pool. What is very nervous for the people, because in the swimming pool, of course, when you are in the water, the noise is more disturbing. Basically, in this case, the only solution was build a wall, 30 centimeter wall with inside a double layer lead. So of course, this also is expensive. The wall, unfortunately, is not possible 90 degree. The wall need an angle, because if the wall don't have an angle, the sound go immediately outside. And the door also is a bigger issue. So in this case, need to project a door very heavy with a double neoprene for sealed everything, and sound absorption inside. So all wall is covered with acoustic plaster, and the door is with a special material for reduce the sound. And of course, this is very expensive, very, very expensive. There is other solution, more simple and also very cheap when it's possible. So when you install, basically, one, the most important, is the Venturi pipe. Venturi pipe is very usually everybody use in the hotel. Basically, the Venturi pipe change the diameter of the pipe. So you change the velocity and you reduce the raw number. So basically the turbulence. So you reduce the turbulence inside the pipe. And in this case, you reduce the noise, and also you stop the pipe resonance. Another way is basically what you use in the organ, a pipe, just a pipe. In the organ, you have a different type of pipe with different diameter, and you have some sound. You can use exactly the same way. The name is Helmholtz resonance, where you have a pipe with a special design, and this pipe just open in the space, reduce some frequency. So for example, when we have the 17 kilohertz frequency in the room, you just can use a typical resonance. For example, there is a famous company produce this type of tube, also nice aesthetically. You put this pipe in your room, and this pipe delete the 17 kilohertz. The name is Helmholtz resonance. It is very cheap. It's very economical. It's possible to do with all different type of material. This is the Venturi, exactly. So you have a different diameter, and you change the velocity and the pressure of the liquid. This is an example, a measurement when you have a typical noise and you make the attenuation. So the attenuation is with the wall, or you use a resonance. Because when you use the resonance pipe, it's very effective, but only precise the frequency. The attenuation is basically for all spectrum. So if you see the spectrum of the noise, you look the spectrum of the sound attenuation, is only the energy is reduced, but the spectrum is basically the same. In fact, you have the same peak. When you use the Helmholtz resonance, change completely the peak. And basically, you delete all high frequency. This graphic, for example, is the case I use 8 different resonance. So with 8 different frequency, all in a high frequency. So basically, cut completely all frequency up to 100 Hertz, or you have only a very little energy. And I leave the all energy down 30 Hertz, because down 30 Hertz is very difficult. You need a very large pipe. So with a Helmholtz, it's very difficult to do down 30 Hertz, but also it's not very useful because 30 Hertz is very low frequency and it's difficult going resonance at 30 Hertz. But it's very important we cut completely the 70 Hertz and the 150, 170 Hertz. And also if you leave, for example, in this case, we have 200 Hertz, 300 Hertz, 500 Hertz, and around 800 Hertz. But it's not a problem because this frequency don't put in resonance nothing. So you don't listen. This is a big difference about the Helmholtz resonance.
So another point we wanted to emphasize about these Helmholtz resonator is that they're completely passive devices. We're not talking about a power device that needs to be plugged in and needs to generate anti-noise or anything along those lines. This is a passive device that sits in your room and it will absorb all of the noise, or most of the noise at that particular frequency. It's just a question of tuning the Helmholtz resonator to match the frequency that you want to try to remove.
Yeah, absolutely. In the past, for example, it's very famous what the Greek done in the theater is just the amphora with the oil, and you change the quantity of the oil to tune the frequency. Also, the Japanese, when made the theater, have basically a cylinder in also in ceramic, in this case kaolin, of course, and this big cylinder positioned down to the stage increase or reduce the voice and basically tuned the sound for the space. It's a very ancient method. It's very, very old method. The only problem is very difficult to simulation. So you need the engineer basically by here around.
So what we've done on this next slide is we've taken the noise that was generated on the roof of the apartment building with the problem. And we've simulated what it might sound like with different forms of acoustic treatment. And shall I?
Yes.
Start? So, okay, so this top chart here, this is the plot of the acoustics measurements that we took in that apartment building. And we're going to play you what that sounds like on site. So I'm pretty sure maybe someone could nod for me just to confirm that you can hear that. Try this again. I'm pretty sure, I can't see any responses, but I'm pretty sure you can hear that. It's quite an
Yes, very well.
Fantastic, thank you. Okay, so
this is if you make a 30 centimeter wall, so very huge wall with a 2-layer LED, this is a noise. So basically, it's the same noise, but with a very huge attenuation, and of course without any high frequency. And this you need amplifier a lot. Is the same but with the pipe. So I don't know if you listen because.
So this one does such a good job. You may not be able to hear it at home. If you turn your volumes up, you might find you can hear it. But it really is dramatically quieter than any of the previous two. So significantly quieter.
Yeah, in reality, the quantity of the energy is not very different, but because the all energy is only down at 30 hertz, basically nobody here, and maybe also the computer not have enough driver to listen. So it's a very big different concept. One concept is reduce the energy. The other concept is shift the energy in a different range.
Okay, to try to draw things together. Sorry, did you want to say anything else? So try to draw things together then. What we found is that basically the noise impact of heat pumps is not related to the type of system. It could be either split systems or monoblock or air-to-air heating systems. And any of these three could generate vibrations and intrusive noise in homes. The point is, though, it's not enough just to take the manufacturer's dB that they've measured in a soundproof room, because they don't pick up the vibrations and the resonances that happen in real life situations. So you need both a quiet heat pump, and it needs to be well installed. It needs to be installed in a way that mitigates the noise risks. And then the third point is that when it comes to designing and installing a heat pump system, you need to consider noise early on. And if you fail to do that, you might end up with really serious problems, like this instance we talked about, where there was a top floor apartment where the people actually had to leave and had to move out for more than a year. They were unable to use their apartment. And you can imagine that brings very, very high cost and all sorts of subsequent problems. And then the fourth point we wanted to make is, if you do end up with some kind of problem, that there are opportunities for not just huge physical barriers, but also these passive solutions, like the Helmholtz resonator.
Yeah, no, for me, what is very important is think also the very huge problem about the children and the pet, because honestly, several times, friend or client, I listen the high frequency just because I listen the high frequency. And when I take out the high frequency, immediately resolve several problems. So I think it's very important to also, it's possible just use a telephone. Today it's very simple to measurement the noise. Just take a free app in your telephone and look if in your house or in your garden you have some strange pitch noise. It's very important for the life. I don't know, for me, maybe.
Great. Thank you. We'll happily take some questions now.